So in the last lecture we discussed about the generation of amplitude modulation, and in which we discussed two methods. First was your square law modulator and second was switching modulator. So we saw that in both the method what is the condition of carrier frequency and how do we generate AM signal. So now we understood the method of analysis or the procedure to analyze a non-linear device. So on the basis of that we have 2 to 3 questions that is asked in GATE, and that type of question you should be able to analyze or you should be able to solve. So the next 3 questions, that is question number 28, 29 and 30, that you can try to solve, and if you are not able to solve it, then you can see how I am proceeding in this question, and you can learn from the approach that how to analyze any non-linear device. And whenever there will be a non-linear device, and how do we take the Fourier transform of that device of that particular term that we have seen in the square law modulator. So I am discussing the question number 28, and the question is, in the system shown in figure A, MT is a low pass signal with bandwidth W and the frequency response of the band pass filter H of f is shown in figure B. If it is desired that the output signal Z of t equal to 10 x of t, the maximum value of W should be strictly less than. We have to find the value of W, and there are two figures. In the first figure there is input signal m of t, and after passing it through some amplifier and band pass filter we are getting some output, and the output should be 10 times of x of t. So let us draw the given diagram first. The input to this amplifier is x of t, which is mt cos 2400 pi t. So it is given, this is the block diagram. The response of this band pass filter is ranging from 700 to 1700. It means that it will pass the signal which lies in this range 700 to 1700. The negative side of the filter can also be drawn, which is nothing but the mirror image of the positive side. And it is also given that the signal m of t, is having the bandwidth W. So we can draw the spectrum like this. It is given that a signal is having low pass signal and bandwidth W, so we can assume any spectrum. We are assuming a triangular signal. We always use this particular spectrum to analyze, and this is the bandwidth. The bandwidth of this signal is W as given in the question. Okay. Now this mt is multiplied with cosine term and it is generating x of t, and this x of t is passing through this amplifier and generating 10 xt plus x square t, which is y of t, and this y of t is passing through the band pass filter, and the output should be 10 times of xt. It means that this filter is suppressing this term x square t. So first of all we should know what is the x of t or spectrum of x of t, and then we will draw the spectrum of x square t, and we will combine these two spectrum 10xt and x square t, then we get the spectrum of y of t. So once we know the spectrum of y of t, from the spectrum of y of t we can we can observe or we can calculate what are the frequency component present in the y of t, then only we can decide what frequency component will pass through the band pass filter and what will not pass through the band pass filter, and according to that we can decide which will be the output of that band pass filter, and our output of this band pass filter should be 10 times of xt. So we have to place this band pass filter in such a way that this x square t term should be suppressed, then only we will get this 10 of xt. So they see x of t, that is the Fourier transform of mt cos 2400 pi t. So let's calculate the Fourier transform of mt cos 2400 pi t. So we know that if mt is having Fourier transform m of f, which we have assumed, then mt cos 2400 pi t will have Fourier transform amplitude divided by 2 and m of f minus the frequency is 1200, so m of f minus 1200 plus m of f plus 1200. This will be the spectrum of x of t. Now if we draw this, x of f, m of f minus 1200, so the spectrum will be at 1200, it will shift to 1200 and this will be 1200 plus w and 1200 minus w, and the mirror image of it. Minus 1200 plus w and minus 1200 minus w. This is the spectrum of x of t. Now we have got the spectrum x of t. Now we have to draw the Fourier transform of y of t, that is y of f. So xt is having Fourier transform x of f, so we will get this spectrum as it is in the spectrum of y of t, and also we will get this spectrum of x square t. So what will be the value of x square t and its Fourier transform? So if I take Fourier transform of x square t, so this will be m square t and cos square 2400 pi t, and we can also write m square t is 1 plus cos 4800 pi t divided by 2, and we can write m square t by 2 plus m square t cos 4800 pi t by 2. So to calculate or to draw the spectrum of this x square t, we have to calculate the Fourier transform of this x square t. So if I take the Fourier transform of this, so this is the Fourier transform of m square t and this is the Fourier transform of m square t multiplied with cos 4800 pi t. So what will be the Fourier transform of m square t? Because m of t is having bandwidth w, so m square t will be having bandwidth 2w. We have seen that if we multiply the signal in time domain, then it will be convolved in frequency domain, and whenever we convolve two signals, then the resultant signal will have maximum frequency which is equal to sum of individual frequency terms. So if m of t and m of t is multiplied in time domain, then m of f which is having frequency W and M of F which is having frequency W are convolved in frequency domain. So its maximum value will be 2 FM. So whatever will be the order of this M of t, that times bandwidth of message signal will be the frequency of that particular term. So if m square t we are doing, so we will be having the spectrum which is extended up to 2W. So this will be having frequency up to 2W because mt is having frequency W, and this will be having frequency, it will shift to the carrier term, or here the carrier term is 2400. So this will be 2400 plus minus 2W. Its frequency range will be 2400 plus minus 2W, and its frequency range will be 2W, because again I am telling you that if m square t we write, that means m of t multiplied with m of t. If I take Fourier transform of m square t, that means we will get m of f convolved with m of f, and the resultant signal will be having frequency, its frequency is W, its frequency is W. So the resultant signal will have the frequency addition of these two frequencies, so W plus W will be 2W, and that's why this m square t will be having maximum frequency 2W. So if we draw the spectrum of this x square t only for positive frequency, Fourier transform of x square t, only for positive frequency I am drawing. So this is 2W, and this will be shifted to 2400. So this is 2400, and this is 2400 plus 2W and 2400 minus 2W. So this is the spectrum of x square t. Now we have the spectrum of x square t. So now we have the spectrum of x square t and the spectrum of x of t, which is spectrum of x of t, and this is the spectrum of x square t. So if I take the if I add it together, then we get the spectrum of y of t, which is output of amplifier. So if we add this, we get this term 2W, we get this term which is 1200 and 1200 plus W and 1200 minus W, and we have another term twenty-four hundred plus 2W and 2400 minus 2W. This term is because of m square t by 2. This term is because of m square t cos 4800 pi t by 2, and this term is because of x of t or x of f, which is mt cos 2400 pi t. So we have these three terms, but what we required at the output of this band pass filter, so at the output of this band pass filter we need 10x of t. 10x of t, that means this term only. We required this term only, and we have to suppress these two terms. These two terms has to be suppressed by this band pass filter. So what we can think is, because the band pass filter we required, so band pass filter is having frequency ranging from 700 to 1700. So we can think that, suppose I am taking it as case 1, we can think that because I want this particular band of frequency, if I place the band pass filter here, which is ranging from 700 to 1700, if I put band pass filter here, this is the response of band pass filter, this is the minimum value 700, this is the maximum value 1700. So if I keep the band pass filter here, then this signal will pass and these two signals will be rejected. We can think like this only, and if I do this, then this 1200 minus W should be equal to 700 and I get W equal to 500. Or I can also equate it 1200 plus W should be equal to 1700, and from here also W is equal to 500 Hertz. So first I can think like this and I get the value of 500. I am getting some value of 500. Now I have to check that whether this value of W is correct or not. So here I am getting the W equal to 500, and if I put the value of W in this particular spectrum, then what I will get is, you will see what I am getting is, now if I put 500 here, so 500 into 2 is 1000, so it is extending up to 1000. If I put here 500, 1200 minus 500 is 700, so this is 700, this is your 1200, this is 700, and this is 1700. If I put here 500, 24 into 500, 24 into 500 into 2, that is 1000, so 1400. This is 2400, this is 3400 and 1400. So what we can see that this red spectrum, which is our desired term, is overlapped with the spectrum of m square t by 2, and this term, this spectrum is also overlapped with the spectrum of this m square t cos 1400 pi t by 2. So if I take W equal to 500, we are not getting exactly 10 xt, we are not getting 10 xt because this is the spectrum of 10 xt, but this 10 xt is distorted in this portion of spectrum because this is overlapped with this term or this term. So we are not getting the undistorted 10 xt. That means the W equal to 500 cannot be the correct answer. So this will not be the correct answer, because if I take W equal to 500, then my signal is overlapped with the other component. So what we have to do now, how can we get this signal 10x of t without distortion? So let us take another case, because now we can think that second we can think that then, because when W is 500, the signal is overlapping with the corresponding with the other components, then we can think that how to avoid this overlapping, how to avoid this overlapping. So this overlapping can be avoided. To avoid this overlapping, this spectrum should be separated with this spectrum, and this component should be separated with this component. So this 1200 minus W should be greater than 2W, then they will not overlap, right? Case 2, you can think that because in the case 1 the components are overlapping with each other, that's why now we can think that if the spectrum does not overlap, then our problem will be solved. And for non-overlapping, this 1200 minus W should be greater than 2W. So 1200 minus W should be greater than 2W, then it will not overlap. And from here also we are getting some value of W. 3W is less than 1200, or you can say W is less than 400. So we have to calculate maximum value. So the maximum value is 400 because the W should be less than 400, that means maximum value is 400. So if I take W equal to 400, then the spectrum will look like if I take W 400, then this is 800. 1200 minus 400, that is also 800. So starting from 800, 1200 plus W, that is 1600, and 2400, this will be centered at 2400, this will be centered at 1200, and this is 400, 3200. So it is our desired term 10xt, and these are undesired term. So now it will pass through the band pass filter. If I take W equal to 400, then these signals will not be overlapped to each other, but it will pass through the band pass filter, and the band pass filter is having frequency range 700 to 1700. So what we observe in this figure is our 10xt is passing through the band pass filter without distortion, but some extra component is also passed through the band pass filter, and these extra components are this portion of other frequency component. Means we will get 10xt plus some extra term, but our requirement was only 10xt. This extra term should also be avoided. This extra term should also be avoided, and it should also be non-overlapped. So now what will we do? Because these two cases are not solving our problem. Now what will we do? So we will consider third case. Now in case 3, because this component has to be passed through the band pass filter, and this component should be rejected by band pass filter. So better to keep band pass filter in such a way that only this component pass through the band pass filter and this component should be avoided. It means that the lowest frequency of band pass filter should be greater than 2W. Should be greater than 2W. That means if I keep my band pass filter here, the lowest frequency of band pass filter, which is 700, it is greater than 2W, then this band pass filter will reject this component. And now I am saying that the highest frequency component of band pass filter should be less than the lowest frequency of this component, and this lowest component is 2400 minus 2W, and this highest component, it is 1700. This value 1700 should be less than 2400 minus 2W. Then this spectrum is also suppressed and this spectrum is also suppressed, and we get only 10xt term, only this x of t term. That means we are saying that 1200 minus W should be greater than 700. So we get 1200, not 1200. This 2W should be less than 700. That we are saying that this frequency component should not be passed, and for this 700 should be greater than 2W. So 700 is greater than 2W, and we are getting W less than 350. So maximum value of W is 350. or you can consider other case, and the other case we are saying that this term 1700 or the maximum frequency of band pass filter 1700 should be less than 2400 minus 2W. So from here also we are getting 2W is less than 700 and we can say W is less than 350 or maximum value is 350. So this is the case when there is no overlapping between these two spectrum and also no extra term is present at the output of band pass filter. Hence we can say that our final answer or the maximum value of W is 350 Hertz. So our next question is question number 29. Let C of t is equal to AC cos 2 pi FCT and M of t equal to cos 2 pi FMT. It is given that the FC is very greater than 5 FM. The signal CT plus MT is applied to the nonlinear device whose output V0 t is related to the input VIT as A VIT plus B VI square t and A and B are constant. The output of nonlinear device is passed through an ideal band pass filter with center frequency FC and bandwidth 3 FM. To produce AM signal, it is desired that to produce AM signal. So we are using a nonlinear device and we are adding the carrier and message signal. So it is very much similar to the method we had discussed, that is a square law modulator. In that method also we added the message signal and carrier signal together and passed it through the nonlinear device. And the characteristics of nonlinear device which we considered in our discussion is same, because we also consider the up to the square term only and the linear term, and in the question also it is given the linear term and the square term. So the analysis or the result of the square law modulator and this question will be same. And the bandwidth is 3 FM. The band pass filter is having a bandwidth 3 FM, but we took the bandwidth of band pass filter as 2 FM. So does it pass any extra term? So it does not pass any extra term, because the carrier frequency, we have seen that the condition for the carrier frequency in case of a square law modulator, the condition to avoid extra components was FC very greater than 3 FM or FC equal to 3 FM. If the carrier frequency is 3 FM, then no extra component can pass through the band pass filter if the bandwidth was 2 FM. But here the FC is very greater than 5 FM, and that's why even if I took the bandwidth of band pass filter 3 FM, it does not allow any other component other than this amplitude modulated waveform. Clear? So you can think of because we have analyzed it, so you can also analyze whatever be the condition is given to us. You directly write CT plus MT and you apply it to the nonlinear device, and you will get some output V0 t which will be having frequency components. You draw the Fourier transform of that particular V0 t, and then you see whether it is when we pass it through the band pass filter. So what are the frequency component passing through the band pass filter. Okay, so I have done this workout, and that's why I am able to say that we will get the same result which we got in case of square law modulator. So that's why I am not deriving it again, because the condition is very much clear, and it is clearly mentioned that the condition for carrier frequency is not even equal to 5 FM, it is much greater than 5 FM. That means our amplitude modulated signal will be separated with other components, and at the output of band pass filter we will get the pure AM signal. It will not distorted by other components present in the input of band pass filter. Okay, so we have to calculate the ratio of A to B, and when we pass it through the square law modulator, the expression is given in the form A1 AC plus 1 plus 2 A2 by A1 MT cos omega Ct. So this is the case, but when we consider the characteristics V naught t is equal to A1 VIT plus A2 VI square t, then we get this result. Here this is A and B, so this is equal to A and this is equal to B, that means A2 is B and A1 is A, and we have to calculate the ratio of A to B. Now the message signal and the carrier signal is given, so the carrier signal Ct is AC cos omega Ct and the message signal Mt is cos 2 pi Fmt. So this term is, on comparing with the standard expression, we know that this term will give me the value of Ka, which is amplitude sensitivity, that is 2A2 by A1, and in our case it is 2B by A. Now there is another condition which is given, that if it is desired to have the sideband power of the AM wave, this is first condition, sideband power of AM wave is half of the carrier power, then because the message signal is single tone sinusoidal, when the message signal is single tone sinusoidal, then the sideband power is given by PC MA square by 2 and it is half of carrier power. So this carrier power will get cancelled and we get modulation index equal to 1. This is our second equation which we are getting. So we have got the value of modulation index which is equal to 1, and the modulation index is defined as K into maximum value of Mt, and in case of sinusoidal signal K into AM we can say, for single tone sinusoidal signal K into AM, and the value of AM means the amplitude of message signal, so this is the Mt, so amplitude of this message signal here is 1, message signal is having amplitude 1, that means MA equal to Ka, or from equation number 1 we have K equal to MA is 1 from equation number 2, and from equation number 1 K equal to 2B by A. So A by B is equal to 2. So the ratio of A to B is 2, and according to option, if we go to the option, then the correct answer is option D. So this is very simple question. If you remember this result for the linear and non-linear term. If there are only two terms, that is linear term and square term, then you can directly use the result which we derived in the generation of AM, that is square law modulator, and whatever is the condition given to you, according to that condition, if you solve step by step, you will come to the result. Okay, so in this way you have to solve the questions. Now next question is question number 30. So next is question number 30. A double sideband suppressed carrier signal is to be generated with a carrier frequency Fc equal to 1 MHz using a nonlinear device with input output characteristics V0 equal to A0 Vi plus A1 Vi cube t, where A0 and A1 are constant. The output of the nonlinear device can be filtered by appropriate band pass filter. Let Vi, which is input to the nonlinear device, is AC dash cos 2 pi Fc dash t plus Mt, where Mt is message signal, then the value of Fc dash is. See, in this question a nonlinear characteristics is given, but this nonlinear device characteristics is not same as we discussed in the last question and also in the theory, and that is in square law modulator. So in this type of question we have to analyze it again. That means the question is going to be a bit lengthy because we have to derive, and here we have to keep in mind that we have to generate double sideband suppressed carrier, and is double sideband suppressed carrier is having center frequency, that means it will be center about carrier frequency 1 megahertz. Okay. So, whatever will be the double sideband suppressed carrier signal generated, its center frequency should be 1 megahertz. That means any because this is double sideband suppressed carrier, so we know about the double sideband suppressed carrier because we have discussed the type of AM, and we also know that the double sideband suppressed carrier will have only upper sideband and lower sideband, and there will be no carrier component. That means carrier at carrier frequency there will be no component. It does not mean that the carrier frequency is not there. The component is not there at particular frequency. The range will be from the FC minus FM, which is generally a lower sideband, and FC plus FM, that is upper sideband. So, the range is from the lower to upper, but exactly at the carrier frequency there will be no component, that is the carrier is suppressed. Okay. Now, according to the question, we have V naught equal to A naught Vi plus A1 Vi cube t. So, Vi is given, Vi is AC dash cos 2 pi Fc dash plus mt. So, let us substitute that value of this A Vi, which is AC dash cos 2 pi Fc dash t plus A naught mt plus A1 AC dash cos 2 pi Fc dash t plus mt whole cube. Now, we will expand this, and after expanding we will get number of terms, and this number of terms will give a number of frequency component, so that we can decide if we want to generate double sideband suppressed carrier, then what should be suppressed and what should be considered by band pass filter. Because whenever we talk about the filter, we should always know that what is the input to that particular filter. It may be a high pass filter, band pass filter, low pass filter. So, whatever will be the filter is given to you, first of all we should always know what is the input to that filter, what is the frequency present at the input of filter, then only we can decide what are the frequency component will be present at the output of that band pass filter. So, first of all, what are the frequency component present in this particular signal V naught? For that we have to expand this signal and then taking the Fourier transform. So, if I will expand this, I get cos 2 pi Fc dash t plus A naught mt, and this is A plus B whole cube. So, this is A1 AC dash cube cos cube 2 pi Fc dash t plus A1 m cube t plus 2 A1 AC dash cos AC square cos square 2 pi Fc dash t mt plus 2 A1 AC dash cos 2 pi Fc dash t m square t. This is A cube plus B cube plus 3A square B, that is 3A square B. So, this is 3A1 A square B and 3AB square. So, these are the terms we will get, and here also we can expand this cos square theta and cos cube theta. So, for this let us write the formula first. So, cos square theta can be written as 1 plus cos 2 theta divided by 2, and we can write cos 3 theta is 4 cos cube theta minus 3 cos theta. So, this is the formula for cos 3 theta and cos square theta. So, let us apply this formula in this equation. We will get V naught equal to A naught AC dash cos 2 pi FC dash t plus A naught MT plus A1 AC dash cube cos cube theta can be written as cos 3 theta. So, this is cos 2 pi 3 FC dash t plus 3 cos theta. So, 3 cos 2 pi FC dash t divided by the whole term is divided by 4. Here I am applying this formula. Cos cube theta is cos 3 theta plus 3 cos theta. So, cos 3 theta, that means if there is 2 pi FCT, that means that previously the frequency was FC dash, then cos 3 theta will have frequency 3 FC. So, that is why I write 3 here with this term FC dash, because it means that the frequency is thrice and here the frequency FC. And then next term is A1 m cube t. Then we will get 3 A1 AC dash square cos square theta. So, 1 plus cos 2 theta, that means 2 pi 2 FC dash, because cos square theta, that means cos 2 theta, and cos 2 theta means the frequency is twice. So, the frequency is 2 FC dash divided by 2 into MT, and the last term plus 3 A1 AC dash cos 2 pi FC dash t into m square t. Or if we expand this one more step, I can write A naught AC dash cos 2 pi FC dash t plus A naught MT plus A1 AC dash cube cos 2 pi 3 FC dash t divided by 4 plus A1 AC dash cube into 3 cos 2 pi FC dash t divided by 4 plus A1 m cube t and 3 by 2 A1 AC dash square into MT plus 3 A1 AC dash square cos 2 pi 2 FC dash t divided by 2 into MT, and the last one is 3 A1 AC dash cos 2 pi FC dash t m square t. So, to know the frequency component, let us draw the Fourier transform of this term, which is very simple. We can easily draw this spectrum, and I can directly write answer from there also, but I want to explain you very clearly. That is why I am taking the Fourier transform, I am drawing it, then I will identify what is required, what is not required, and then only I will come to the answer. Okay. So, first term is having cosine term. So, cosine term, the Fourier transform of cosine is impulse at FC dash, impulse at FC dash, first term. Second term is MT is having Fourier transform m of f, this is our first term, and m of f, that means it is extended up to Fm, this is our second term. This is third term, A1 AC dash cube, all are constant, cos 2 pi 3 FC dash, that means the impulse at 3 FC. So, we will get impulse at somewhere here at 3 FC. This is our third term. And the fourth term is A1 m cube t, that means the message signal is having frequency FM, so m cube will be frequency 3 FM. So this is up to 3 FM. This is our fourth term. Fifth term is having empty, that means the same term, so it will add with this second term. So second and fifth term will be added together and amplitude will be increased. So this term and this term we can add. Here the empty is multiplied with 2fc dash, cosine having frequency 2fc dash. So empty Fourier transform is FM and it is multiplying with the cosine signal, so it will shift to the frequency of cosine, and frequency of cosine is 2fc dash, so it will shift to 2fc dash here, 2fc dash, and this will be 2fc dash plus FM because the message signal frequency is FM, and this is 2fc dash minus FM. This is your sixth term. And the last term, m square t multiplying with cosine, and cosine is having frequency fc dash. So cosine is having frequency fc dash and m square t will be having frequency 2fm. So that spectrum which is extended up to 2fm will shift to fc dash. So it will shift to fc dash, means here it will shift. So we will get fc dash plus 2fm and fc dash minus 2fm. Now you can easily identify what are the frequency component present in the filter. So these are the frequency component in the filter, input of filter, and at the output of filter we required double sideband band pass filter. We required double sideband suppressed carrier signal. So we have to find in this spectrum which is double sideband suppressed carrier. So double sideband, that means it should have frequency component higher than carrier frequency and lower than carrier frequency, and double sideband suppressed carrier, that means the carrier at the center frequency it should not have any other component. So as we can see that this third term is having only the carrier frequency, so it cannot be our answer. This is having center frequency 0 and there is no sideband, right? This is not called sideband, this is a low frequency signal. This is having pure message signals which is having frequency FM and 3 FM. So this cannot be our answer. So in this term, the first term and seventh term, if we see that there is some carrier frequency component, that is fc dash, and the component is also present here at fc dash, and there is some frequency which is known as higher than center frequency. So fc dash plus 2fm and fc dash minus 2fm, it means that this is our lower sideband, this is our upper sideband, and this is our carrier term. So it is called double sideband full carrier because carrier is also present. At center frequency there is a component. Now if you observe this, then there is a center frequency but no frequency component is present at 2fc, and there is some frequency higher than this center frequency, that is known as upper sideband, and this is known as lower sideband, and there is no frequency component present at 2fc. There is no component here. At 2fc there is no component, there is no impulse, so that's why it is known as double sideband suppressed carrier. So this is our desired term, and by appropriate band pass filter which is given in the question, we will select this particular term only. We will place the band pass filter in such a way that it will pass this particular term and it will reject all other term. It will reject all other term and it will pass only this term. So this double sideband suppressed carrier is generated in this way, and this double sideband suppressed carrier signal should have center frequency 1 megahertz, and this double sideband suppressed carrier signal which we have generated is having center frequency 2 Fc dash. So this center frequency 2 Fc dash should be equal to 1 megahertz, then Fc dash equal to 0.5 megahertz. So this is our desired result. We had to calculate the value of Fc dash, and according to the option, the correct answer is option C.